Okay, we're now going to do our inference review with means. I just did one in regards to proportions that should be posted right next to this. So means deals with chapters 10 and 11. So if you want a more extensive review of that, you can go scroll down and find the videos from chapter 10 and chapter 11 and look at those. So obviously you can go to Khan Academy and watch the inference and confidence intervals and hypothesis tests with means. But anyway, so there's a total of 4 inferences with means that you have to be able to do, and that's with one sample. You could do a one sample t-test for a mean, or a one sample t-interval for a mean. And then with 2 samples, you have a 2 sample t-test for the difference in means, or a 2 sample t-interval for the difference in means. So those 4 things are what I want to try to review right quickly here, and also talk about some side issues that that could come up. If you have any questions, please let me know, and please send them to me. I'll be glad to address them. And of course, this is there's a worksheet that should be posted near this, that this is designed to review the stuff so you can do the worksheet. But let's look at this one. So last year, the time it took workers to assemble a calculator in McGill's calculator factory was 8.2 minutes. McGill wishes to see if this time has changed in the past year. He takes an SRS of 50, of the workers, and finds that their mean time for assembling a calculator is 7.8 minutes, with a standard deviation of 2.9. Is there statistically significant evidence that the mean assembly time has changed in the past year? Perform an appropriate test. Also, create a 95% confidence interval. Interpret the interval and interpret the confidence level. Then make the connection between the confidence interval, the p-value, and the null hypothesis. So this is the sort of things that get asked about on a free response problem in the AP Stats exam. This is kind of combining a number of different things. So, but the first thing that should stand out to you is the fact that this is quantitative data, and you're dealing with the mean. So it talks about finding the mean time. So who is mean? And that's Mr. T. When you're dealing with means, you're going to do a t-interval or a t-test. You also notice it's a simple random sample of size 50, and with means, this makes us happy in 2 ways. First of all, our most important condition of randomness is met, but also we have normality because of the central limit theorem, because our sample size is bigger than 30. So anyway, well, first of all, it asks us, is there statistically significant evidence that the time has changed? Perform a test. So we do the THAME acronym: the type of inference, the hypotheses, the assumptions, the mechanics, and the ending. And so we start, whenever we do a test, the first thing we do is we state what we're doing. And so in this case, this is a one sample t-test for a mean. That is the name for it. So that's what you have to say. So actually, if you wrote the formula down, you're going to get credit for that anyway. But the easiest thing to do, I think, is to state what you're doing in that regard. And so then we have our hypotheses. So our null hypothesis here is whatever the claim is of the problem, or the status quo. And it said of it here, it used to is 8.2, and he wants to see if that has changed. So this is what we're testing: 8.2 minutes. Make sure and put the units. Then the alternative is what we suspect might be true. The null is whatever's claimed, all right, or whatever we're testing against. The alternative is what we're suspecting. Nowhere in here does it say we're suspecting greater than or less than. So we go with not equal to. So this is a two-sided test. Obviously, you have to define what mu is. It is in the meantime it takes all of his workers to assemble a calculator. All right, so for the whole population, never put x bar here, and never put p hat. It's always mu or it's p. All right, so anyway, and so then we send. Then we do our assumptions. So that's the type of inference. That's the hypotheses. Our assumptions we send. So the first thing, like I said, it says that an SRS was taken, so random conditions met. So that's good. Our population size has at least 10 times our sample size for independence, because we're not using replacement here. He's just taking these 50 out. And so that ensures us our formula for standard error will work. And then lastly, normality. In this case, our sample size is bigger than 30 by the central limit theorem. Normality is met. Now remember, with means, it's a little complicated in regards to normality. You have 3 possible ways of getting it. Number 1, is the sample size bigger than 30? It is here, so you got it. But if that's not true, number 2, it could possibly say in the problem up here somewhere that things vary approximately normally. And if that case, you would say it says up there that it varies approximately normally, therefore normality is met. But if it doesn't have that either, we go to the third option. And that is we would graph the sample data, which we can't do that here because we weren't given the data. We would graph it as long as we don't have outliers or strong skewness, we feel good about normality. So, please remember that. And of course, the actually more complete way of saying this is because our sample size is bigger than 30 by the central limit theorem, the sampling distribution of the sample mean is approximate normal. That's actually the more complete way, but this is sort of the quickest way you can say it. All right, but that's your assumptions, that's your sin. And so now we go to the mechanics. We need our test statistic and our p-value. And with t, remember, you have to have degrees of freedom. And so here's our formula for our test statistic. And I'll just go ahead and show you how to use your calculator, and then we'll talk about the formula. So this is the way we can quickly find our test statistic and p-value. And so what we'll do is we'll hit the stat button, and we will go to tests, and then we'll go to t-test right there. So we go to t-test, and then we're using stats here. We weren't given data, so we're given stats. So our hypothesized value is 8.2. Our x bar is our sample mean, and our sample mean here is 7.8. So I would go 7.8, and then our sample standard deviation is 2.9. And then our sample size is 50. So right like that. And then our alternative here is not equal to. So I can do that, and we do calculate. And so there is my t-test statistic. There's my p-value, write p-value. And then with t's, you always make sure and write down your degrees of freedom, which is your sample size minus 1 for the one sample t inferences. So that's how you do the mechanics. Now, having said that, if you're asked to show your work on the formula, which could happen, so remember the formula on your formula sheet for a test statistic is at the bottom of page 1, standardized test statistic minus parameter over standard error. Our statistic here is our x bar. Our parameters, our hypothesized parameter, which is our 8.2. All right, and so then the standard error of the statistic, well, we go to the next page. The standard error, the sample statistic for a mean down here is s over the square root of n. And of course, that's for the two sample thing, which we're going to do an example like that in a minute. So that is, and so entering those values in, you would enter it like that. Statistic minus parameter over standard error is equal to that. Now, to find your p-value, given your test statistic, you'll use a CDF function. And so what we will do, in order, if we were doing that, is we will go second distribution and go down to TCDF. Now, in this case, it's a negative number, and we have a two-sided test. So we are going to go less than, we're going to go outside of that and multiply it by 2. If it said less than here, we just go less than. Or if it said greater than there, we just go greater than. But we're going less than and multiplying by 2 since it's a two-sided test. So we go TCDF, and so it's negative infinity to negative 0.97532. And then our degrees of freedom is sample size minus 1, 49. And so then we go like that, boom. And so that is that, but it's a two-sided test. So I go times 2. And there's the p-value. So so that is sort of doing it by hand in essence. Okay, so there's your mechanics. Make sure and write down all three of those numbers, and then you do your conclusion with a p-value, just like we've been doing for a while now. This p-value is greater than 0.05, so I do not reject the null. There is not convincing evidence that. And then you restate the alternative in context. That the mean time it takes all the workers to assemble a calculator is not equal to 8.2 minutes. And there you go. That is how you do a one sample t-test for a mean. Now, you could be asked to interpret, that is drawing a conclusion with a p-value. To interpret the p-value, it's to state it as a probability, as a conditional probability. So if you're given the instruction to interpret the p-value, you would say, well, given the null is true, in other words, given the mean time is actually 8.2, the probability we would get a sample value as unusual as 7.8 or more unusual is about 33.42% of the time. That is interpreting a p-value, stating a p-value as a probability. Okay, so that's that. Now, before we go, let's finish this. So this also, okay, we got to find the interval. Okay, so it says also create a 95% confidence interval. So to get the confidence interval, what we would do is this. Of course, with confidence intervals, we do the TAME acronym. We don't have the hypotheses, but the type, it would be a one sample T interval for a mean. Our sinning would be the same thing that it is up here, all right? And then our mechanics would be this interval, all right? And then our ending is going to be we're 95% confident the interval captures the parameter. But this is how we do this. So we would say stat, we would go test, and so this is a one sample T interval, which is just going to be T interval, the 8th option. T interval. So I hit enter on that, and of course it entered the data for me because I just did the test on it. And this is a 95% I do believe, 0.95. And so then we do calculate. And so there's our interval right there. And so to interpret that interval is this. I'm 95% confident that that interval captures mu, the mean time it takes all of the workers to assemble a calculator. So that is interpreting the interval. That's drawing your proper conclusion. Interpreting the confidence level is, if we were to do this same procedure many times and made many intervals, 95% of the intervals would capture mu, and you say what mu is, the mean time that it takes all the workers to assemble a calculator. So that's interpreting the confidence interval, interpreting the confidence level. I also want to remind you of the formula for confidence interval. So the formula for confidence interval, because that could be asked of you. Well, so there's the generic thing, confidence interval, statistic plus or minus critical value times the standard error of the statistic. Okay, well, our statistic here is, going to be x bar. Statistic's x bar, okay? Plus or minus critical value, that's our z star or t star. It's the number of standard errors. There are intervals going to the left and to the right. T star, so we'll find that. And then the standard error, well, what is that? Well, once again, that's off of your little formula sheet. The standard error is that guy, s over the square root of n. And so it would be s over the square root of n. And so in this particular problem, so you remember it's set up in the problem 7.8, all right, plus or minus. What is our t star for 95%? Well, what you could do is you could use inverse t, which I'm not going to show you that right now in the interest of time. But remember this table B, it has the critical values for t and actually for z. As you go to 95% here, and you would go above it now, 95% right there. Now, the lowest line is the z star. Everything above it is the t stars. So that would be for t star. Now, and you go to the notice on the left side, it has the degrees of freedom, sample size -1. So for 95%, you would go up. And in this case, we have 49 degrees of freedom. And so you would just go to the nearest one, go to the 50, so 2.009. If you wanted to, you could prorate it between that and that. We'll just use 2.009. So this would be 2.009. And then the standard deviation of our sample is 2.9 over the square root of 50. That whole term, remember, is the margin of error. So that is a common question that we've done many times. How do you find the margin of error? Well, that's going to be 2.009 times 2.9 divided by the square root of 50. And so it in fact is 0.824 approximately. So 7.8 plus or minus 0.824. And so that is our margin of error. Margin of error. So anyway, and that seems reasonable looking at our interval over here. Okay, so that's just a quick little reminder on how to use the formula to find your confidence interval. And then let's see, what else did we have to do? The other thing was to make the connection between the interval and the p-value and the hypothesized value. And to do that, you would just say, well, that interval captures 8.2. 8.2 is our hypothesized value. So therefore, 8.2 is a plausible value for mu. It should not be rejected. And that's exactly what our high p-value. The high p-value, 0.3342, also tells us to not reject the null hypothesis value. So that's making the connection between the interval, all right, the interval, the hypothesized value, and the p-value. Okay? And that's a popular question. So, okay, so that's a quick little rundown of you know, a one sample deal with means, and then in the confidence intervals. And the only thing left in inference is the two sample inferences with means. So the two sample test, the two sample interval. So let's look at an example of that. McGill wishes to see if there's a difference in the mean times it takes his workers to assemble a graphing calculator and a scientific calculator. He takes a random sample of 60 of his graphing calculators and finds they have a mean of that and a standard deviation of that. Okay. He takes another sample of 70 of his scientific calculators and finds that they have a mean of that and a standard deviation of that. Okay. Perform a test of significance. And so the premise here is, well, it appears that they are really different, 10.4 and 9.1. But is that difference between the graphing calculator time and the scientific calculator time, is it plausible that difference is due to sampling variability? All right, and so these are certainly means, and so we're going to do a t-test. And there's two samples, so it's a two-sample t-test. But also we're asked to, once again, create a confidence interval and to make the connection between the interval, the p-value, and the null hypothesis value. Okay, so let's do this problem. Now, one other thing I want to say to you, notice the reason we're having to do t here and we can't use normal CDF, we can't use normal calculations, is because these are the sample standard deviations. And the same thing occurs here. With back in the one sample thing, notice this is the standard deviation of the sample of those 50. Okay, it's not of the whole population. And so we're using two estimates, x bar as an estimate for mu, and this s as an estimate for sigma, the population standard deviation. And these two estimates create more variability. So we can't use a normal curve anymore. We have to use a t-distribution. So if we did know sigma, like a chapter 7 problem, it would say, hey, you know, the population's varying with this mean and this standard deviation, then we could use normal CDF. So that is a bit of a technicality there. But anyway. All right, so we're asked to perform a test here. We got two samples. We know their means. We know Mr. T is mean. So it's a two-sample t-test for the difference in means. So we do the THAME acronym to do our test for the difference in means. So that's our name. Then our hypotheses. With the two-sample stuff, you know, the null hypothesis is always that they're going to be equal or that their difference is 0. The alternative here, it does not say greater than or less than or imply anything up here. So therefore we go not equal to. All right. And it's not considered ethical to say, hey, it's taking the graphing calculators more, so I'll go greater than there. No, you can't look at the sample data. It has to be hinted at somewhere else in the problem. So then you always define your variables. So mu sub g is the mean time in minutes it takes the graphing calculators to be assembled in its factory. And mu sub s is the scientific calculator. So it's the whole population, all of them, not just these 60 graphing and these 70 scientific. All right, and then we sin. Now this is a two-sample deal, so it is I sin. All right, and so in other words, independent random. It says that random samples were taken, so independent random conditions met. That, of course, the random samples ensure that we get a representative population, helps even out the influence of any variables going on. All right, here's independence. There must be at least 600 graphing calculators and 700 scientific for our population size at least 10 times their sample sizes, because we're not using replacement here. And then lastly, both sample sizes are bigger than 30, thus by the central limit theorem normality is met. But the same thing applies here. If they're less than 30, you'd look and does it say they vary normally? If it does, you can say we had normalities met, or you graph both of the samples, and both of the samples have to not have outliers nor strong skewness in order for normality to be reasonable. Okay, so anyway. All right, and so there's your conditions, and then so there's your formula with your t-test statistic and your p-value. Let me show you how to get now this one. There's a very complicated formula for that, but you just get it off your calculator. And if you don't have access to your calculator, just use the smaller sample size -1. So here the smaller sample size is 60. You would just go with 59. And so a lot of times these answers will be a bit off because of that, and that's okay. But this is how you get this answer with your calculator. So you would go stat, you would go test, and this is a two-sample t-test. Option 4, 2 sample t-test. So you go like that. We're using stats here, and so so our first mean is 10.4. Okay, and our first standard deviation is 2.6, and then our first sample size is 60, and then our second mean is 9.1. Our second standard deviation is 3.7, and our second sample size is 70. So of course those numbers were all listed up in the problem there. They were all listed up in the problem there. So so anyway, so okay. Now, so what you would do, the alternative is not equal to. We always say no to pooled whenever our calculator asks, and then we hit calculate, and so there's our test statistic p-value and our degrees of freedom. So those three numbers you have to write down, and so there they are. And so anyway, so that formula, by the way, once again, if you look at your formula sheet, you do need to be able to work with these formulas. And so our standardized test statistics, statistic minus parameter over standard error. Well, here we got two statistics, and so we subtract them. Now our parameter is effectively 0 here because we're sort of assuming that the two population values are the same, so we say 0. And the standard error of the statistic, well, I'll turn that over here, and there it is. There it is for the two samples, right there. And so that's, I just entered those values in there and got that, and then you could do TCDF from 2.3415 to infinity with that degrees of freedom and multiply it by 2 to get that. But of course now you would have to use an estimate for degrees of freedom if you didn't have that function on your calculator. And then we have our p-value statement, which this p-value is less than 0.05. So I reject the null. I have convincing evidence that and then you restate the alternative. I have convincing evidence that the mean times for assembling the graphing and scientific calculators at this factory are different. So, so in this case, there does appear to be a statistically significant difference. And then lastly, it asks us to make a confidence interval for the difference. And so what we would do is we would go stat, test, and this is a 2 sample t interval. So a 2 sample t interval, 2 sample t interval is right there, 2 sample t interval. So I hit enter, and so we are working with stats, and there are the stats that I just entered. Confidence level 95%, always say no to pooled, hit calculate, and there's our interval. And of course, to interpret our interval, if we were doing the TAME acronym, is I'm 95% confident that the true difference is in there. Okay, that the difference between our parameters in there, and say what they are. And say, you know, the difference between the mean time that it takes the graphing calculators to be assembled at this factory and the similar mean time for the scientific. And so that's the interval. And your mechanics for the interval, you would just put the interval and the degrees of freedom. And but then the other thing this problem asks us to do is to make the connection once again between the interval, the hypothesized value, and the p-value. This interval does not contain 0. Whenever you have these two sample things, in other words, you're dealing with the difference. The big deal to us is 0 in the interval. It does not contain 0, so it is not a plausible value for the true mean difference and should be rejected. The low p-value also tells us to reject that null hypothesis, which I restated here as a difference. And so that's it. Now I do want to show you one other thing. And that is when you're given the data. Like both of these problems that I did in this video is when you're given the stats. And let me remind you, what if you're given the raw data? Like for instance, let's say, you know, your context here is where it has been claimed that the mean of a bunch of test scores is 75. And so we decide to test this. We suspect that the actual mean is less than that. So there's our alternative. And let's say here's our sample data. Here are our x values that we get. And so are these values, okay, is the average of these values so different from this, it would give us reason to reject the null in favor of the alternative. Well, and so what we would do is we aren't given the stats here, we're given the data. So we will put this in list 1. So we will go stat, and we will go edit, and put all those values in list 1. Okay, and now we'll do a t-test with that data. And so we would go stat, test, and do a t-test, in other words, a 1 sample t-test. And then we're working with data now, And so our null hypothesis value is 75. We put our data in list 1. Frequency is 1. The alternative here is less than. And so we would go calculate. And so there it is. And so there's our test statistic p-value. And so it's 0.19. So we would not have statistically significant evidence to reject null because that's greater than 0.05. And we do not have convincing evidence that the mean of the test scores is less than 75. Even though our X bar was 73.857, which is less than 75, in this case, it's not statistically significantly less. Now, of course, we could have just committed type 2 error, right? Now, that's a whole other subject in the world of stats that we could review another time, type 1 and type 2 error and power. So maybe we need to, in which case, if in fact the null is false and we failed to reject it, we could need some more power. We need, and how do you get more power? Mainly by increasing your sample size. And it's a really small sample size, so maybe we just didn't have enough power and we need to increase our power. But I don't want to start rambling too much. But there you go. That's your little review of inference. And so give that worksheet a try, and please send me any questions that you have.